That's better. All right, 3D printing for prototypes. So I've got 5 big categories, and then we'll look at each one of them. So there's just the setup that you need to do, or maybe you call it tuning, that you need to do on your printer to have the best chance. So there's a couple of things I'll go through there. Most of those we've actually already looked at one way or another, but I'll put them in here just so that it's in a whole list, because you do need to do that, otherwise all the other stuff is not going to make much sense anyway. Let's see, second I put the orientation of the print. So when you create a model, you can print it in any orientation you want to, and there are some that are better than others, and it depends on what you're trying to get out of the model. I've got a couple of things in what I'm going to call the assembly category. So when you're putting this thing together, you might have just printed it all as one piece, and is an option in some cases, but probably you're going to have to put it together and assemble it somehow, so there's some things for that. Then I put a category in here for strength. A lot of times you're printing a part that, a prototype or whatever, that isn't necessarily going to do the function of the final thing you're making, but you want it to get close, and so there are better and worse ways to make it strong enough to do whatever you want it to do. And then I put surface finish as the last thing. Sometimes it matters what are you trying to make a prototype that looks nice or functions nice, or both, or neither, or who knows. But so I did put that in there. So before we do any of those things, it's probably important to realize that maybe this is number 0 over here, is that you don't have to print everything. So there are a lot of hardware pieces that you can interface with your printed parts. Some parts you can just purchase. Some things, some common shapes, it's much simpler to go buy a dowel versus printing a round cylinder and kind of stuff. So first thing is that not everything should be printed. And it's okay, in my mind, I assume it would be okay in most people's minds, that you can mix and match. You can buy some parts and then put them together with printed parts. We see this a lot, not as much as once upon a time, but in the printing lab downstairs, somebody wants to print like a box or whatever, and maybe there's a reason you need to print a very custom box, but probably not. It's probably still going to be better in the end if your end goal is some kind of box enclosure thing, to buy the box and modify it to do what you want it to do, than to print a box. Sometimes it makes sense to print a box, but not always. Not everything needs to be printed. And then the other thing you need to remember, so this will be 00, is that you're probably never going to get, with these style printers, you're never going to get a part that is like machine shop accurate. So I'll call it that. It's very difficult, and to the point that it's not practical. And I'm going to just put this in quotes. You can get close, and it depends on, is that good enough for what your end goal is, or not. And so if you're just making a aesthetic prototype that's going to look like kind of the thing that you're trying to demonstrate to somebody, then that's probably fine. If you're making a part that you're using your printed part to verify the model, and it's got to interface with all these other parts, you will get information in general, but you won't be able to get down to the couple of thousandths of an inch that your part actually represents what the machine part would look like, or size-wise it would be. So you can get useful information from your printed part, but don't count on it. If it doesn't plug right into the spot it's supposed to, don't automatically assume that means that if you were to machine this part, that it wouldn't fit either. You know, it might actually be the right dimensions that you have in place, but there's a lot more variables in printing something versus machining something. And don't assume that if you draw something in CAD and it fits together in the SolidWorks assembly, that it's going to come out perfectly from a mill and be exactly those same dimensions, just because that's not going to be true either. It is very difficult to hold tolerances when you start getting down into you allow for no tolerance in your design. So so this setup and tuning, most of this stuff we have hit on at one point or another in the quarter, because you kind of had to do it to get going. But it is, if you just plug your printer in and start printing, then there's a very good chance that you're definitely going to not get machine shop accurate parts, and the parts that you print probably won't work together very well unless you built in a whole lot of slop in your design to start with. So there's some relatively easy setup things that you can do to have a better chance of having parts that interface with one another correctly. So the first thing, this will be the tuning section. First thing is the E-steps. So this was the idea that you tell the printer to extrude a certain amount of filament, a length of filament, and the control board sends a certain number of steps. So the steps on the stepper motor, remember our stepper motors are NEMA 17. Pretty much, I don't think any of you have printers that don't have NEMA 17 stepper motors, and they have I think it's 200 steps per revolution. So a 1.8 degree step size. And these are the steps that E-steps refers to. There are steps for X, Y, and Z also. Those generally are less likely to be off, because unless you have a slop in your system, you know, it's got a loose belt or whatever, or you're accelerating super quickly and you're skipping steps, so the stepper thinks it moved and it didn't actually move, then probably the X, Y, and Z steps are accurate, or at least really close to accurate. But the E steps, they a lot of times do need to be calibrated early on, and so we did go through and calibrate on this printer that's sitting. This is an Ender 3 with the unified firmware on it. I don't think you can actually go in and modify the E-steps from the control panel of the printer, at least with the firmware it's running right now. In general, you can do that, but even if you couldn't get to it from the control panel, you could go in and talk to your printer directly and change it, you know, using something like Repetier Host, where you can send G-codes directly to the printer over your USB cable. So you can get to there even if you can't get to it from your control panel. You don't necessarily have to go in and re-upload firmware for it. But you do have to interface with it somehow. And most printers you can do that through the control panel. Other printers you might have to connect a USB cable to do that. So this E-steps will make sure that you are actually extruding the length of filament that you expect to be extruding. So it's because it's really easy to over extrude just because your stepper motor on your extruder is tuned to have too many steps for millimeter or inch or whatever units you're using of filament, or too few and you're under extrude. So it's really an easy thing to tune off the bat. Kind of related to that, also on the filament size anyway, but much simpler to do, is just be sure that you measure your filament diameter, because this will have the similar effect. Right now, pretty much every printer, and all the printers that are in the 200, 250 and under price range, have no sense of how much filament actually left the nozzle. It knows, the slicer has told it how much filament should leave the nozzle, And based on that and just a conservation of mass principle, it goes in and calculates how many steps to turn the extruder that would put out that volume of filament. But it's assuming a filament diameter, it's assuming your E-steps are calibrated correctly, and it is less likely now that your filament is way out of spec, but obviously the cheaper filament you're using, the more likely there is variations in the diameter of the filament. Your slicer probably, unless you have changed it, is expecting 1.75 millimeter diameter filament. There's some that expect a little bit larger, closer to 3 millimeters. I don't think any of you have that particular printer, but most of them are expecting this. And if your filament is a larger diameter or a smaller diameter, the printer and the slicer don't have any way of knowing that unless you tell it that, hey, I'm actually running filament that every time I measure it, it is 1.8 millimeters. And that might be enough difference. Seems really small, but it might be enough difference to cause an over extrusion because you're putting more mass in than the slicer thinks you're putting in. And so that's an easy one, that you change that in your slicer. So you don't even change anything on your printer unless you change the filament. But you change that on your slicer before you even create the G-code to send to the printer. So that's an easy one to do. And like I said, you don't normally need to do the X, Y, Z steps, but you may want to. You may want to check them, tell it to drive a certain distance across the bed and measure did it actually go that far, just to see. But there is another thing that's similar to that I'm going to call, we'll call it calibrate X, Y. And this is doing that same thing a different way for a different reason. So when you measure the actual movement of the printer, you're measuring, as whatever the resolution of whatever you're using to measure has. But when you actually print, it prints out this line that's, probably for you 0.4 millimeters wide, and there might be some variation on between where the slicer wanted to put that line and where the printer actually put that line. And it might cause holes or walls to be a little bit off from where they were supposed to be, in the neighborhood of a couple of tenths of millimeters possibly. So what you do with this is create you a little rectangle. Doesn't actually matter what the dimensions are, but it doesn't have to be a rectangle, just some simple little shape, maybe I don't know, what did I write down, 15 millimeters. If you make too small of moves when you're calibrating on any of this stuff, then you're not going to get as accurate. Like if I'm trying to calibrate my E-steps and I tell it to extrude a millimeter of filament, then that's probably not going to be as good as telling it to extrude 50 millimeters of filament, because I'm not averaging a lot of variables together when I just do one little tiny movement. So do something, relatively large, but it doesn't have to be huge. Something in this range. Maybe you have walls that are, so we're going to put a wall, I don't know, maybe 3 millimeters or something, so they're not super tiny. Just something in that rough size, and then go measure the thing. So it's sort of like the calibration cube, the X, Y, Z little cube that you print, and you could even use that. This one will also give you an interior dimension, though, so that you can measure an inside wall. And then there is, and I don't know what it's called in every slicer, but in Cura, there's one called, let me see, I wrote it down, horizontal expansion. And it is hidden by default, so it's not going to be one that you just find. But let's see, I think I have Cura open. Yeah, so over here, if you go in and just type horizontal, well, there it is. It's in the shell section of things, but you can get to it from just typing horizontal expand, or HO even. And what this does is it can be a positive or negative number. And so if you measure, this is supposed to be 20 by 15, and you measure and it comes out to be 20.2 and 15.1 or whatever, then you are over the dimension. So you're overdoing the dimension, and you can put in a negative horizontal expansion and it'll shrink in the dimension. So you can kind of tune holes and boundaries in the slicer side of things without having to go in and try and tune, and even tuning your X and Y position on your bed and motion on your printer may not actually affect this. It just gets it in the right spot, but you still have to squirt out that filament and it lands maybe not quite where you wanted it to. This actually will go in and adjust for moving those walls around in the slicer side of things. So in the geometry side of things, it will move the walls around. So it can either move them out, so if you have a positive horizontal expansion, or it can suck them in a little bit if you need a negative horizontal expansion, you're printing too big. So that can be one way where you just create some, and you can have a whole bunch of these shapes, maybe some circles and some rectangles or whatever, and kind of average out what is going to be your best horizontal expansion. But that's on the slicer side of things, and that is one way that you can probably get in there and at least start to get parts that are accurate enough that you can, put bolts through holes correctly and things like that, and make parts interface with other parts without overlap or a gap. So that's that horizontal expansion. Other slicers have a similar thing. They just call it different names, and I don't know all the different names. But in Cura, this is Cura, they call it horizontal expansion. The other thing is, this is kind of in the tuning, and it's a effect called elephant foot. And what this is it's basically when you print those first few layers, maybe I'm printing that box right there, then the first few layers are really squished down. So here's the bed, and you end up with the first few layers being really close to the bed, and so it makes these bottom layers a little bigger than the other layers. So that's the elephant foot. I guess it kind of looks like an elephant foot, sort of. So there's basically two ways that you can deal with this. Well, three really. You could just shave it off. So you can actually go and get a oh shoot, can't think of the word. When you want a deburring tool. You can get a deburring tool, and it'll kind of help with this. You can use a knife and kind of just remove the squished out part. Now the other thing it has done though is, since those first few layers, I don't know how many, maybe this is 3 layers worth or just 1 or 2 layers worth, you have also squished them in the Z direction, so you've lost a little bit of your Z height on that part also. So if that's a critical dimension, then you've lost that one, or at least you've shrunk it. If you're printing a part where this is going to be an issue, then the easiest thing to do, it takes more time and filament, but the easiest thing to do is print on a raft. So in Cura, you tell it, instead of printing directly on the bed, you're going to print on a raft. This will take longer because basically it builds this little 5 or 6 layer platform underneath however big your part is. So it does use more filament, and it does take longer because it has to build the raft. But now, instead of your part being squished, your raft will be squished, and you don't care about it. You peel it off at the end anyway, so you don't care about that. And you have a better chance of the Z dimension and the bottom of your part being more accurate. So that's one thing you can do. Obviously, you can try and tune exactly how close your print is. So if you can get that first layer just right, then you have a chance of getting it, to not squish down to begin with. Now, then you run the risk of, if it's just a little too high, it might not stick very well. So the part comes sliding off. There's one other thing you can do. It's a little trickier, but when you design your part, design it with a tiny little chamfer on the bottom. so that when you squished it down, it goes back out to the right size. So you can kind of just preemptively say, I'm going to squish these layers, but they're going to be chamfered in, so when they squish out, they're more or less back where I wanted them. You'll still lose some of your Z height, so you do have to, if you think you're going to have, two or three layers of squish that are smaller than the other layers, then you might have to make your part a couple of layers taller than it normally would be. A lot of these things, though, like if you do this just to get the part to come out right, you're changing your original design file. So you're not necessarily, you wouldn't actually make this part in the machine shop. So this is more a way to fix it just so that the printed part does what it's supposed to do. I think those are all the ones that I wrote down for tuning. Those are some of the biggest ones. There are lots of little tuning things you can do, speeds and speeds and feeds, I guess, basically on this apply just the same as they would on machining something out of metal. The idea that applies anyway. Making sure your machine itself is square. We talk about leveling the bed, but you don't ever actually put a level on it because you're not making it level to the ground. You're making it square within itself. So making sure that your machine actually is square is important. I've put the BL Touch on this one, so it can actually print on a tilted bed, but that means the part is going to come out, kind of weird if it's got this. It's a printed right, but it's printed on a crooked surface. It may not print the way you want it. I've seen some printers where the little brackets that hold, let me see if I can, so you've got your gantry and your axis across here. Then there's two little brackets, one here and one here. I've seen some printers where this bracket was thicker than the one on the other side, so it was spaced out more, and that what that does is this axis across the middle, if you look at it from the top, is running across there, not this badly, but it's running across there, not parallel to the front edge of your bed, and so it thinks it's putting a straight line across there, but it's actually putting a sloped line across the front of your part. And so all these actual parts of your printer, you need to make sure are actually square. Otherwise, you're going to get, it may print fine, but it's going to print a part that was printed with a mechanism that wasn't square, and so it won't be square. So that's another thing that is not as obvious, but if you keep getting parts that just don't fit together, it might be the printer itself is not square in some sense. Maybe your bed down here is crooked. Got a lot of spring on one side and it's squished down on the other side. And so you'll get parts that print on there, even with the BL Touch. It'll figure out that bed's crooked and adjust for it, but your part's still going to be crooked. All right. So those are on the tuning side of things that you can go in and tweak to get a better representation. And that's probably, as far as getting printed parts to interface with other parts, those are probably the first things you should try and do. The other thing is to always, if your part that you're going to print has to interface with other parts, whether they're store-bought or other printed parts, you probably should build in somewhere in the neighborhood of 0.3 millimeters tolerance into the parts that you're going to print, just because there's always going to be a little bit of that line ended up a little bit more extrusion than another or whatever, so you're probably not going to get below 0.3 very easily. Remember, this is you can do the little test where you print the cylinders. I think there's a part that's kind of like this, and then the part is actually, I don't know, some shape, and this has holes in it with different gaps between the parts, and whichever one yours will print and have come loose, that's pretty much your minimum gap that you can put in a part and expect your printer to reproduce. And so some of them are going to be more or less bonded together, and you're not, that gap, whatever it was, 0.1, is just too small for your printer. And maybe this one is also bonded, so 0.2. Maybe this one you're just starting to break, you can actually break this piece of loose, 0.3. So 0.3 is maybe your minimum tolerance that you can expect to achieve between holes and things that go in the hole. And so you can print one of those parts. That's one of the assignments to do, is print one of those parts anyway. And you'll know what this number is when you go to design stuff. All right, so another thing that affects your printed part working as a prototype is just the way you orient it on the build plate to begin with. So in general, whatever your most critical dimensions are, whether it's a hole that has to be a certain diameter, or the outside of a perimeter that has to interface with some other part somewhere, identify the most critical dimension or dimensions, and those need to be parallel to the bed, because your most accurate movement is parallel to the bed. And in some cases, most of your printers, the bed does move back and forth, so that makes your X dimension more accurate than your Y dimension, because your X, the print head's moving back and forth in X, and it's relatively light and easy to change directions, where the bed is more massive than the little print head, and so it's a little bit harder to change directions in the Y direction. So if you're narrowed it down to one specific thing, then your most critical dimensions need to be in the X direction. But normally, I'm thinking of circles in general. If you need to print a hole or a peg or something that's round, that really does need to be parallel to the bed. Sometimes you can't get around it. You have holes in both in perpendicular planes, so one of them has to be in the Z direction. But in general, anything parallel to the bed is going to have a better chance of coming out the actual shape and size that you wanted it, versus if you print it stacked up in the Z direction. Always remember that this isn't necessarily orienting, but it is totally fine to print in multiple pieces and then glue them together later, or snap them together, or bolt them together. Sometimes you have critical dimensions that are just not going to be compatible with one another, and so maybe you print in multiple directions. Print in multiple parts would be a better way to say that, and then assemble later. That can be as simple as when you bring the part into Cura or whatever you want to slice it with. If any part that you embed below the surface of the virtual bed in Cura just doesn't get printed, so it's like you sliced it in half. So you can, that also works if you're printing really big stuff. Just put it, only the part that you want to print right now above the bed, and print just that part. Probably though, that's not going to work in every scenario unless it's a very simple part. Probably you're going to have to take either design in multiple parts or go over to something like, I generally use Mesh Mixer, slice the thing up, and then print all the individual parts. Also with orienting, this kind of goes in with the strength category too that I had later, but do remember that FDM or FFF, whichever, the kind of printers that you have, when you print using this technology, it's going to be anisotropic. Just the way that the process works. You're printing layers on top of layers of plastic, and so you're going to almost invariably be weaker in shear between those layers. In general, material is weaker in shear, but now it's weaker in shear because you have these boundary layers between every layer. you can, if you're trying to print something that needs to be strong in multiple directions, one thing you can do here is what I did with the little bracket here. You can print, and it does take a lot longer, print all top layers. So in your slicer, you tell it to print everything as a top layer, so it takes a little bit longer and prints them completely solid. So that's one way you can make it a little bit stronger. You can print a little bit hotter. I guess this is going into the strength part, which we'll just refer back to this. So in general, the hotter you can print, so you've done your temperature tower, so you know where your filament falls apart at. But the hotter you print, then in general it will be a little bit stronger. It'll probably be not as nice on the surface because you're oozing a little more and it's a little blobby maybe. But if the more important part is the strength of it, then you can print a little bit hotter. You can over extrude on purpose. So you can, in the slicer, you can have your extrusion or your feed rate set to 105% maybe, you know, instead of 100%, or if it's 1, then 1.05 or whatever your slicer uses for the feed rate on the extruder. And so you can do all of those, and that's a way to basically, you're making sure that the layers really squish together, they're hot when they do squish together, and they have a better chance of actually melting together. You are going to get a worse calibrated part, so it's going to be over extruded. Obviously, if you tell it to over extrude, it's going to be over extruded. The hotter temperatures will make it a little less predictable on where it lands when it actually cools. And the all top layers doesn't have as bad effect on the surface finish as these other two does. So if you want a part that's just generally kind of strong, then maybe just do all top layers and not the other two things, and it'll still have a decent surface finish without some of the problems these other two might introduce. You can still get good parts if you did all three of these, and they'd be probably as strong as you possibly could make them with printing, 3D printing. Obviously, again, on the, I guess this is more on the strength style things, there are different materials. So you've probably mostly printed in PLA. PLA is great because it's one of the lower melting temperatures. It's relatively easy to print. You don't have to have an enclosure. You don't really have to have a heated bed. Most of you do. But it's a little bit more on the brittle side if you need this part to be any flexible. So there are other materials. There's one called, I haven't really used this, I think it's ASA. It's kind of a in between PLA and ABS, but it prints a little more like PLA. So it's one, I haven't used it a lot though, so I can't really comment on it. ABS is one that is more, just a little bit more flexible material, but to print it is more difficult. So you do have to have a heated bed. You probably need an enclosure to enclose the whole chamber so that the whole chamber gets heated up. And if you don't have those things, then ABS has a bad tendency of not sticking together at all. It'll actually peel apart on its own. The layers would peel apart. So it's a tougher material. Maybe if you don't want to deal with either of these, then but you need something that's a little bit more robust than PLA, try PETG. It's not too difficult to print. I will warn you that if you're printing on a glass bed and you're printing PETG, you need some kind of release layer. So if you ever get into it and you see the PETG option in Cure and you got a sample of it or a roll of it, don't just throw it onto a glass bed with nothing in between there. You need some kind of release layer, or else it will pretty much just stick to the bed and not come off. It will rip the bed particles off with it. And the release layer is not complicated. It's like a glue stick. You know, that can be all it is. But without that, PETG will have a little bit of issue releasing from the bed. Also, with PETG and the fact that it does really like to stick to printer beds, you don't want to squish that first layer a whole lot, because it does stick pretty well to particularly glass. Smooth surfaces it sticks well to. So you don't want to squish it as much as you would PLA. So we kind of turned this into orienting the part where we're talking about trying to get the dimensions correct to more in the strength side of stuff. So that's okay though. We may have repeated ourselves later on. Then it comes to assembly. So it is possible, in fact, one of the optional assignments for here is that you print what's called a print in place part. So it has some kind of features that are captured hinges or ball joints or whatever that basically print all in one piece, and then assuming that you have done your tolerancing correctly, it can snap loose and articulate. So you can print joints in place. You just have to be sure you know what your tolerance is. A really common one is just a pin joint. You can easily build a part that would have a hole and then a pin built into the other part. That could all be one thing, assuming your tolerances are correct. Now, this one has a little problem though. So the orientation that you would want to print this in is more or less what I have here, so that you get your circles accurate. But when you do that, this pin is printed, in layers this way. So it's going to be really weak and sheer. So you do have to want to bulk up. If you want to print one of these, you want to bulk up the pin so that you don't have these little tiny sheer circles stacked on top of one another. And if you print this laying flat, now your circle here and the circle that creates the pin itself are printed in layers, and you'll probably will have a tough time getting those to consistently separate when you go to break it loose. But you can get it to work, and so that is one option, is just print everything in place. There's some really cool models that one guy has done of cars and things like that are print in place, and you snap them all together and assemble it as one piece. Obviously, probably much simpler than that is just glue the thing. So super glue works really well. Oh, I meant to didn't bring it. Super glue works fine. It's more on the brittle side of stuff. Epoxy works really well, but it's you have to account for the fact that it takes up space. It's thick. They do make. I have to look it up. I think it's 3D Gloop. Does anybody know if that's the name? See, that's the name of it. All right. So it's a company that makes basically a liquid that dissolves PLA, and so this stuff will basically chemically bond your parts together by dissolving them and remelting them together, and it's 3D Gloop. I have some. I haven't actually used it, but they do have some of that. That's for PLA. ABS actually just melts with acetone. So if you are printing, you've got your printer set up in a way that it can print ABS, then you can melt it with acetone, just from Walmart or wherever. So it's much simpler. But PLA does not necessarily melt the same with acetone. It uses a different chemical that's inside this 3D Gloop, among other things they put in there, I guess. But it is a thing that if you really need something to be permanently bonded together, then that is a product that you can try out. I have, where'd I put them? I have some of these. Let's look at this. Oh, it's tiny. So these little guys, there we go. This little guy right here, right there, is a insert. It's a threaded insert, so you probably can't see inside there, but there are threads like that would match up with a screw. They come in all different sizes. This is, obviously a smaller one. But the point of these guys is that you print a hole and you insert the metal threads into that hole. These particular ones are heat set, so they do make a little tool that you can basically put on the end of your soldering iron, and it'll fit in there and kind of distribute. Actually, this isn't the right size for this one, but it'll distribute the heat and help it sit in there. You don't actually need the tool. You can use just a soldering iron by itself. And these inserts, there's a heat set. So it's got these little ridges around it that kind of, as you heat it up, it melts the metal, the plastic around it, and then as the plastic cools, it's all inside these little knurls on the outer surface of these threads, and it pretty much well locks it in there against torque and axial pull-out or whatever. So they're pretty good. You do have to be a little bit careful. It's really easy to overheat these things, and it just melts everything. So you want to practice on one of these before you put it on the part that you spent 9 hours printing. You would want to make some of these in practice. But they're really cheap. McMaster, Amazon has them, and they come in all different sizes. The general rule is you want about 2 millimeters of wall around them. So you may want to make sure that your model can support that. You might have to increase the wall count to get it to do that, or build it in a way that it's going to automatically put that much wall around them. They will work with less, but like I said, they do get obviously hot when you put the soldering iron on them or whatever heat source, and they will melt all the plastic around them if it's not pretty sturdy. You can size your hole in a way that you can just tap them in, like just press them in with a hammer or whatever, and they work pretty much as well. They don't have quite the bond with the material around them if you just press them in, but they will at least work. You can get really low tech with a similar approach, and so these inserts are heat set or press fit. The press fit ones, I think they're tapered actually, although you could probably make this non-tapered one sit in there just fine. Low tech version is you use captured nuts. So you print a cavity in your part. I assume it's a hex or whatever. I don't know what kind of you're putting in there, but you put a cavity, and then you use the something similar to stop at this layer, or the little bit of code that we wrote earlier to do the filament change. Somehow you need to tell the printer to stop at this point. Then you literally go get a hex nut from Lowe's, and you drop it in there, and you let the print finish, and it'll print the next layer. It prints over the top of it, and it captures it inside there. Obviously you have to leave a hole for the bolt to go through, but it'll capture it inside there. And so it's super easy and much cheaper. Well, it's not really cheaper than the heat set. It's easier to acquire because you probably have to order the heat set inserts. I don't think you can get them in town anywhere. But these captured nuts, it can literally be just a hex nut from any store, and you trap it in there. You do have to be a little bit careful in that if you are trying to put a lot of torque on these things, then it is very easy for that nut to strip out the hole that it's in, and then it's stuck inside there, and it's spinning, so you're kind of stuck at that point. Obviously, even simpler than that is you can just use some kind of self-tapping screws and build in screw holes that are a little undersized a pilot hole basically into your part, and use a self-tapping screw that cuts its own threads through there. Those you don't get as many undos and reassembles as you might of some of these other with actual metal threads, but you can make a really easy way to assemble it. On most all of these, when you're assembling parts, and this is not necessarily just for 3D printing, but it does help if you have some kind of locating features, maybe a locating ridge or something that helps you locate the part when it goes to match with another part. It does help keep everything together. You can, even with PLA, I'm on my next page here, you can make snap fit parts. They're not going to have as many cycles as possibly any of these others with the metal threads or whatever, but you can create snap fit parts. Generally you make something, this is way out of scale, this is just showing you some features. So you have a relatively easy entrance angle, so a slope here that's relatively easy to slide into the whatever it's snapping into. So 45 degrees, 60 degrees, something like that. And then a much steeper, they usually call it retraction angle, so that it doesn't want to easily back out of the slot that it's fitting. There's a slot somewhere that this thing is fitting into. You do want a fillet down here. This fillet is at least 0.5 times the thickness, so thickness into the page of the tab. Because you're going to, make this thing bend back and forth. You don't have to have this taper over here, but it does help to have the taper. The other thing that helps here, and you can't always achieve this, but it does help if you print these, again, you want them to be able to bend, so it is better to print them, let's draw a smaller one. It's better to print them so that they're, printing this way versus printing this way. So if you have to stand them in the Z direction, they're probably going to break sooner than if you lay them flat parallel to X and Y axis. So this is better, this is going to be weaker. Just because when you're using this thing, it has to bend back some amount to clear the notch. And when you bend this one back, you've got a lot of little shear layers that are probably going to want to come apart. So you can do that, and they'll work a couple of times. I didn't print one of those. I did print a hinge. What to do with it? Oh, over here. I did print some hinges. Printed these little hinges. They're not actually part of anything, but this is PLA, and you can get a couple of 20-ish cycles of movement before it'll snap in half. But you can actually already see that it's there's a stress line there, but it will. You get a couple of hinges motions before it snaps. The key to these is you have to have some relief, and I think this one, this one I printed where this, well, we got to draw the picture of that, it's too small. Oh. So you need some relief on the back side of it, or on the front side, but you need some relief. I printed the one here that is much stiffer in a way to where it actually went in and put 2 full layers right here. So these were printed standing up so that they were stacked on, the layers are stacked on top of one another. And the layers look like this. And so this dimension was, I was printing with a 0.4 nozzle, so this was actually 0.8, and that's probably a little too stiff. The other one works a little better, although I assume it's going to break sooner. And it is a little thinner there. I actually made that dimension 0.6, so I'm doing a 0.4 millimeter nozzle, so it can't actually get 2 full walls in there, but what it did is it printed one wall. We need a bigger wall. Printed one wall, and then when it came to print the one over here, it printed it, it just kind of overlapped them. So it had like 1.5 walls there or something. You could, when it was brand new, you could kind of see that. I don't know if you kind of see it now because it's been up, but that 0.6, yeah, assuming you're using a 0.4 millimeter nozzle, seemed to work pretty well, and it was easier to actually bend to begin with. The other one's still pretty stiff, but if you need some kind of compliance or maybe a hinge that works a couple of times, you can print them even in PLA. They'll work much better in materials that are less brittle, but most of your printers are going to have a tough time printing those type of materials like nylon or something like that, but you can do it. It is possible to do anyway. Let's see, so that was most of the things I had for the idea of assembly. Let's see, the next thing I had was strength, although I think we've actually talked about all of those. Yes, we actually have already talked about all the strength when we were talking about orientation, so no real reason to talk about those again. So the last thing, so 4 was strength, but we already did that. I got ahead. The last thing was the surface finish. So sometimes it matters how the part looks. Obviously, you can go in, primer. If I'm using this, I go to AutoZone or someplace like that and get the high build primer for a car. You have it at Walmart and Lowe's too, I think, but the high build primer, because what it is really thick, and so you can put it on there. Now you'll lose some of your fine details if you're trying to retain those, but put the high build primer on there and sand it, and you have a pretty decent surface finish. You can do all the spot fill and that kind of stuff too, if you really want to make it look nice, or Bondo, although the stuff in the red tube is probably all you really need. That way you don't have to use the hardener with it. You just put it on there and let it dry. And those are all like automotive products. So you can get them at Walmart, but you can also get them at auto stores. I kind of mentioned that acetone will dissolve ABS. So if you are printing in ABS, then you can do a thing called vapor smoothing, and it will basically create a acetone vapor that lands on your part and smooths it out. It melts it and smooths it out. There is a PLA sort of equivalent, so acetone for ABS. And there is a special filament, I think it's called Polysure, that uses IPA, so isopropyl alcohol, and but it prints like PLA. So the Polysmooth. Oh, Polysure is the actual device. All right. There is one down in Bogard. Polysmooth is the material. Now I will say this material is what they've had to do to modify it to get it to react with the IPA. It is very moisture sensitive, so it does not last long out, particularly where we are, where it's very humid. It doesn't last long outside of a container. So you do want to keep it sealed away and dry, because the material just is very hygroscopic. For straight up PLA, you can smooth it, but the chemicals you have to deal with are not stuff you want to deal with without a hood and everything. So, although I think this this 3D gloop, I think they may have, or maybe the 3D gloop itself, you can kind of paint on there, and it will melt the PLA. I don't know. I've never tried that. That does remind me, though. There's a product called, I think it's XTC maybe. It's basically just a resin that you pour on your print, and it coats it, and it doesn't smooth it. It just it creates a smooth layer on top of your print. So if you're just trying to get something smooth, you'll lose a lot of your like nice sharp corners and everything. But if you want it smooth, then that is one way to do it. There's a couple of settings in Cura. So there's an ironing setting. This is in Cura, and the top and other sliders too. But I'm assuming most of you are running Cura. The top layer, assuming the top layer is flat, then it will go in and extrude a tiny amount of plastic, but mainly just iron the top of your print. So it runs the heated up hot end over your print and more or less irons it flat. There's fuzzy also in Cura. I don't know if other slicers even have this, but it does. Maybe you want a texture on your surface, and it goes in. I printed this little guy. He's off a Thingiverse, but he's got the fuzzy layer, and so it kind of, and you can control the depth of it and the frequency of it. But normally he'd be really smooth, but it gives this kind of textured-y surface. Maybe you want a grip or something like that that you want to have distinguished from the rest of your model. You can add the fuzzy feature in Cura, and it basically jitters around as it prints the outer wall. Everything else prints the same, but the outer wall jitters around, and it creates a little bit of a fuzzy surface. And so it gives a different texture that it kind of, you know, it still is in layers, so you still pick up that there's a layer in there, but it does hide the fact that it's 3D printed a little bit. So that's one thing you can do. And then just a reminder that if you want to put text on maybe you have labels you need to embed into the part you're printing, it's better to engrave. So sink them down into the part. So that's better than embossing. So embossing, you raise them up above the thing, unless they're really big letters. But in general, engraving, and you don't even have to sink them that deep, 1 or 2 layers deep. So that way you can bake in text to your part. Maybe it's an on-off location for a switch or something like that. You can bake that into the part. And if you engrave them, then that's it's going to last a little better and look a little better than embossing normally will. Embossing, when you have the raised one, a lot of times they're thin and maybe it doesn't get 2 full walls, or there's a gap in the corner of it or something like that. So normally engraving is going to be better if you're trying to put text on there, like physical text.